This lesson follows on from the previous lesson, which was all about density, and it talks about the solids, liquids and gases, and the particles in solids, liquids and gases, and what happens when they change state from a solid to a liquid, from a liquid to a gas, and back again. So a little bit of basic chemistry to start off with is things are made of particles. Now we talk about particles where sometimes the particles are atoms, sometimes the particles are molecules, but we talk about a particle as being the smallest part of something. That means it is still what it is. For example, the smallest particle you could have with water would be one molecule of two hydrogen atoms and one oxygen atom joined together, because that is what water is. Water is H2O. So the smallest particle of water would be one of those, which is a molecule. If we had a piece of copper and we melted that down, the smallest particle of copper would be a copper atom. So we're talking about particles, the smallest things that you get. Now, in a solid, the particles are held together in a fixed shape. In a liquid, the particles are still attracted together, but they sort of slosh over each other and they take the shape of the container that it's in. And in a gas, they fill the whole container and they're very, very spread out. So that's all basic stuff that we know so far. Now, the reason that this happens is there is a force of attraction between each particle in a substance. So in a piece of ice, for example, all of the water particles are attracted to every other water particle in there, and if these two come together, they will stick, they will bond, they will join together. And what happens is, as the thing heats up, these particles start to vibrate more and more and more and more. They're always vibrating. If you get some frozen peas out of the freezer, they look solid, but in fact all the particles in there are still vibrating, but they're vibrating a little bit less because they're colder. And you have to get things down to minus 273 degrees centigrade, and then they stop vibrating. That's absolute zero. It's as cold as you can get. So anyway, we've got some particles of water which are below 0 degrees centigrade, and so those particles are in a solid. And like I said, the particles are shaking and shaking like that. They're vibrating, but they are still bonded to the particle next to it. If you get it hot enough, the vibrations are so much so that they break apart those bonds that are holding things together, and then it starts to, the particles start to move over each other, and that is what we have in a liquid. So in a liquid, they're still attracted to each other, but they're vibrating a lot more. And then when we get up hot enough, so if it's water, we get to 100 degrees, they vibrate so fast that they break free from their bonds and they fly around all over the place, and then it becomes a gas. And of course, if you cool that gas down, they vibrate a little bit less, and then they can find that they can come back together again, and that gas condenses back into a liquid. And then when the liquid cools down, they're vibrating a little bit less, and then they find they can join solidly and turn back into a solid again. So much for all that sort of basic science that we've had so far. And what we're talking about is when we're heating these things up, we're adding thermal energy to it, and we are increasing the thermal energy store inside that substance. So if it is ice here, the more thermal energy you put in, you increase the energy store. Now, before we go on to something else, let's talk about the difference between boiling and evaporation. If you have a puddle on a warm day, it will dry up, but that doesn't mean that the water in there is boiled and turned into, it's all sort of boiled away and turned into a vapor. It's just some of it evaporates at a time, and evaporation happens at the surface of a liquid. Now, if you were to lick the back of your hand, I've just put some warm liquid on there, saliva from my mouth, which is at the temperature of my body, so it shouldn't feel cold on my hand. But if I blow it with my breath, which is warm, onto this warm water that's on my hand feels cold, and the evaporation takes heat away. And the reason that happens is this. Now, if you have some water here, for example, the water is made of lots and lots of particles, and some of the particles are moving faster than other particles. The ones that are moving faster have got more thermal energy, and the temperature of that piece of water is like the average temperature of all of those little bits and pieces that are in there. Now, the particles that have got more energy, I've shown them with sort of larger arrows here. Some of those have enough energy that they actually can leave the surface of the water. And if that leaves the surface of the water and goes into water vapor in the air, there are now fewer hot particles in there, and so it cools down. And so that's why sweating cools you down and evaporation cools you down. So we're going to break now and do a little experiment where I'm going to look at what happens to the temperature of some ice as I heat it up. I'm going to get some ice out of the freezer, and it's going to be in a little beaker, and that beaker is going to be put into a larger jug, and that jug is going to have some boiling water in there. So the jug will add some thermal energy into the ice, slowly melt the ice, and I'm going to measure the temperature of that ice as it melts and turns into water. So we'll be back in a minute to talk about what we found out with that. Okay, so I have got some ice here, and it is at -8.2 degrees. I am now going to start my stopwatch and add some boiling water to the bowl around the ice, which will cause the ice to melt. Keep the thing upright. Okay, so hopefully we can see that. Right, we got -7 degrees there after 30 seconds. Just move that so we can see. -6.8, 6.7. -6.3 after 45 seconds. It's now going down to -5.5. 52 seconds, -5. Let's have a little look here. So you can see I've got ice in there still. That's the time, that's the temperature, -3.9. So we can plot a little graph of this. So we are on 1 degree, 0.7 of a degree, 0.5 of a degree, still 0.5 of a degree. So the temperature stopped changing, it stopped going up. It's stuck at about ½ degree centigrade, which is more or less the melting point of the ice. So there's still heat going into it, still thermal energy from the boiling water that's around, but you can see the clock is going on. The clock's still going on, and it appears to be stuck at about 0.5 of a degree centigrade after going up quite steadily. Okay. So it's keeping that in there. And now it's going up again. So in that experiment we saw that as we added thermal energy to the ice, as we warmed the ice up, the ice started to increase in temperature from around about -7, -8 degrees centigrade. It got up to around about 0, in fact stuck on about 0.5 degrees, and it stayed there for nearly a minute. And even though the heat was still going into it from the hot water, the temperature wasn't increasing anymore. Then after a minute, then it started to increase again. So if we drew it as a graph, it would look something like this. So it rose for a while, and then it stayed steady, and then it started rising again. And you have to ask the question, why, if we are still putting heat into the ice, did it not continually increase in temperature? It increased in temperature up to this point, but then at this point here it didn't increase for a while, and then after a while it started going up again. Now what's actually happening here is all the energy that you're putting in, it's not going into increasing the temperature, it's going into changing the state, changing it from a solid into a liquid. And then once that change has happened, so at this point here it is all a liquid now, and so then the rest of the energy that goes into increasing the temperature, and then that would continue up and up and up until it got to 100, because it was water, that's the boiling point, and then it would stop again, and it would stop at 100 degrees. And again, even though you're putting more energy in, you can't get the water hotter. All that energy that is going in is just changing the state from a liquid into a gas. And if we could then measure the temperature of the steam, or sorry, it's not steam. Steam is actually water particles. Water vapor is a gas which you cannot see. And if you was to capture that water vapor and then start measuring the temperature, once all the water had evaporated, then the temperature of the water vapor would continue to increase. So if you see a graph like that, you can say this point here, 0, that is the melting point, and this point here, 100, as is water, that is the boiling point. You need to be able to recognize that in those graphs. Right, so that is it for solids, liquids and gases and the changes of state. One thing I didn't mention is that a solid, you cannot compress it. Once it's in a shape, the particles are all stuck together, so you can't squash it into a smaller shape. You can't squash a liquid into a smaller, you can change the shape of it, but you can't fit it into a smaller space. Whereas a gas, because there's lots of gaps between the particles, you can compress a gas into a smaller space. So that's it, and next lesson I shall talk about what happens to all of this stuff, and what happens to all of this stuff, and why if you lick the back of your hand and you blow it, even though you've put warm liquid from your mouth on there and you're blowing it with warm breath from your mouth, your hand goes cold. So that's what we'll be doing next lesson. Thank you.